Hi, my name's Tom Hoeffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about covalent bonding. In the previous video, we covered ionic bonding, so if you haven't watched that video yet, I highly recommend that. I'll put a link in the description. We're going to switch gears here over to covalent bonding. And covalent bonding typically happens when you have two nonmetals. And the reason this is occurring is that nonmetals have high ionization energy, which means they hold on to their electrons really, really well. Okay, they do a good job of attracting electrons. So when a nonmetal bumps into another nonmetal, neither one can win. Okay, so they end up sharing their electrons, and that's where we get this word covalent, because this prefix co means share, kind of like when you're co-captains or co-presidents, you share the responsibility of being the captain or the president. Now the word covalent simply means the sharing of the valence electrons, and this happens when you have two nonmetals bumping into each other, because there will not be a transfer of electrons because they hold on to their electrons really, really, really well. Okay, so that high ionization energy means electrons won't be transferred, but they can be shared, and that's the discussion of today's video. Okay, there's going to be 6 steps to do covalent bonding, and these 6 steps will cover probably even the most complex covalent bonding molecules that are out there. So let's go ahead and get started with our first example. I'm going to do the first one, and then maybe we can do some together. So the first one that we're going to do is going to be NF3. And our first step to do covalent bonding is to sum up the valence electrons. So what I like to do is I like to create a little bit of a chart here. So I'm going to list the nitrogen and the fluorine. I have 1 nitrogen and I have 3 fluorines. And then in these parentheses, I'm going to look at the periodic table and determine how many valence electrons each nitrogen and each fluorine has. Okay, so when I look at the periodic table, I look up and I find out that nitrogen has 5 valence electrons. And since there's only 1 of them, I have 5 valence electrons in the molecule. Okay, I look up fluorine on the periodic table and I discover that it has 7 valence electrons, but I have 3 of them. So that's going to be a total of 21 electrons. Okay, and then when I sum up the nitrogen and the fluorine together, I find out that I have 26 electrons for my problem. Okay, now that I kind of pulled together, I'm going to distribute them based on the rules that I have in these steps. One last thing I want to talk about summing up the electrons is that this number should always end up being an even number. If you get an odd number here, ding, 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 there's probably something going wrong. So that should be kind of like a red flag. The other thing is sometimes these things have a charge, and you do have to consider the charge. If it's a negative charge, we're going to add electrons because they're coming into the molecule. Of course, if this charge was positive, that means electrons would be leaving, and we'd have to subtract a couple electrons. But in this problem, there's no charge, so we don't have to worry about that. And I got that even number, so I think we're ready to go to step 2. And step 2 says connect the atoms with bonds. Now, a covalent bond is just going to be a line or a dash. And that line or dash constitutes 2 electrons. Okay. We have central atoms and non-central atoms in covalent bonding. Your central atom is not always the first atom, okay? However, your central atom typically is going to be the one that's singular. And the one that's singular in this case is going to be the nitrogen. So I'm going to put the nitrogen in the center, and then I'm going to surround it with 3 fluorines, and I'm going to connect them with a line or a dash, okay? And it doesn't matter which sides you pick. I'm going to pick the left, the right, and maybe the bottom for my fluorines. Now, each of these lines or dashes is actually what's representing the covalent bond, okay? And there are 2 electrons in this covalent bond. And these 2 electrons are actually going to be shared between the nitrogen and the fluorine. So they count for both of them. So these 2 electrons will count for the fluorine, and these 2 electrons will count for the nitrogen. So right now in my drawing, I've used up 6 electrons, and those 6 electrons are going to be subtracted from the total. And in my notes, I'm just going to remind myself that I use those 6 electrons for these 3 covalent bonds. There's 2 electrons here, 2 electrons here, and 2 electrons here, which means I have just a total of 20 electrons left over. Okay, where do the electrons go next? So we give them to the bonds first. Okay, the next step, step 3, it says complete non-central atom octets. Okay, so the non-central atoms are going to be the fluorines. Currently, the fluorine has 2 electrons, these 2 electrons. So to complete the octet, it needs 6 more electrons. 1, 2, 3, 4, 5, 6. Plus these 2 will give fluorine a complete valence shell of 8 valence electrons. And I have this saying that's called 8 is great, like chocolate cake. That's when the atoms have their octets or have their valence shell completely filled, and that's a good thing. Okay, I'm going to do that for the other fluorines. 2, 4, 6 plus these 2 electrons gets its octet complete. 2, 4, 6 plus these 2 electrons completes that octet. And if we add up all the electrons that I used on these non-central atoms, I got 6 here, 6 here, and 6 here. That's a total of 18 electrons that I placed on the non-central atoms. Now that's going to leave me with 2 electrons left over. Okay, and step 4 tells us to place the leftover electrons on the central atom. And as you can see, this ends up being a really cute problem, nice and neat. Okay, and I'm going to explain why. Because if we investigate our nitrogen right now, remember these shared electrons count for the fluorine and the nitrogen. So there's 2 electrons here for this nitrogen, 2 more from this bond, and 2 more from this bond. So this nitrogen already has 6 valence electrons. It only needs 2 more electrons to complete its octet. And that's exactly how many I have left over. So that's what I mean by just being a cute and easy problem. So these leftover electrons, okay, are always going to be thrown on the central atom. No matter how many there are, we're going to throw them on to the central atom. And in this case, just everything ends up working out really, really nicely because the fluorine has 8 valence electrons, all of them do, okay? And so does my central atom. It has 2, 4, 6, 8 electrons as well, okay? So in this problem, I did not have to try multiple bonds because my central atom had a completed octet. But if it didn't have a completed octet, I would have to try to do multiple bonds. And you'll see that in a problem or two from this example, okay? And then we have step 6, which is called don't forget your dipoles, okay? When we're talking about this nitrogen-fluorine bond, the way I have it right now, it looks like the nitrogen and the fluorine are sharing the electrons equally. And that's not the case, okay? We know that fluorine has a higher electronegativity than the nitrogen does. It's up and to the right on the periodic table the most, okay? And when elements are up and to the right on the periodic table more, they do a better job of attracting electrons. It's only going to be the shared electrons that are going to be pushed towards the fluorine because fluorine has a stronger electronegativity than the nitrogen. So we have this thing called a dipole sign, okay? Now these electrons are still being shared, but it's going to be unequal between the nitrogen and the fluorine, okay? So the dipole sign looks something like this. We're going to draw it right above our bond to say, hey, these electrons, they're not going to be shared equally. They're going to be pushed towards the fluorine. And I'm going to do that on every single one of my bonds because these bonds are polar covalent. And the word polar on its own means unequal. The word covalent means sharing of the valence electrons. So polar covalent means unequal share of the valence electrons. And our dipole sign is what tells us that the sharing is unequal. So if the elements are different from each other, one of them is going to be stronger than the other, and they're not going to share their electrons equally. The only way they could share their electrons equally is if they're the same identical element. Okay, so that's NF3. Let's go ahead and try a couple more to make sure you have this down. Okay, and I'm going to put a problem on the board. And if you want to pause the video and try it on your own and then unpause it when you're done to check your answer, that would probably be a good idea to work this video in the best way. Okay, so H2O is a problem. Okay, we're just a water molecule. Go ahead and try it. Pause the video, and then when you come back, I'll be working the problem. So first step here is to sum up the valence electrons. So I'm going to create my little chart here. We got 2 hydrogens that each have 1 valence electron. We have 1 oxygen that donates 6 valence electrons. So in this problem, we have 8 valence electrons, okay, which isn't a lot to deal with. So we're going to connect the bonds, connect the atoms with bonds, and this time the second atom is actually our central atom because it's the one that's singular. So I'm going to put that in the middle, and then I'm going to connect it with some bonds to hydrogen. Now remember, each of these bonds makes up 2 electrons, okay? So that's going to be 4 electrons on the bonds. So I have 4 electrons left over, and it tells us the electrons need to go next to the non-central atom to complete their octets, okay? Well, there's something that's very special about hydrogen, okay? Hydrogen only needs a duet to fill its shell because the hydrogen only has an s orbital, and to complete its shell, that first ring, okay, it only needs 2 electrons. So hydrogen really doesn't do the octet rule, it does the duet rule. And if we look here, each of these hydrogens already have 2 electrons because the shared electrons count for both atoms. These 2 electrons count for the hydrogen as well as the oxygen. So each of these hydrogens are already happy. So we're going to use 0 electrons on the non-central atom because their duets are already fulfilled. Okay, so it leaves us 4 electrons left over. We place the leftover electrons on the central atom being the oxygen. Okay, and this is kind of neat because when I place those 4 extra leftover electrons on the central atom, that completes the octet because it already had 4 electrons. So once again, a lot of these problems will just kind of like work themselves out where whatever leftovers you have that go on the central atom, it kind of completes its octet. So it's kind of another kind of an easy problem that we have. So we're going to put those 4 electrons, we put them on the central atom in the end. We have 0 left over, but the problem's not done because we can't forget about our dipoles. So we compare the location of hydrogen and oxygen on the periodic table. The hydrogen's all the way in the top left-hand corner, okay? But if we were to bring it down 1 row, a hydrogen's electronegativity value would fall between boron and carbon, okay? And still, oxygen is still further to the right. So oxygen is stronger when it comes to electronegativity than the hydrogen. So the dipoles this time are going to go towards the center because oxygen's electronegativity value is higher than hydrogen's, okay? And that completes the problem. This is the way that a water molecule would look like with covalent bonding, okay? Our next unit is actually going to be talking about the geometry that this molecule will show, which is not what we're covering in this particular video. So if you want to talk about geometry, you're going to have to wait for a few more lessons after we have covalent bonding, kind of like the fundamentals mastered, okay? So let's go ahead and try a couple more. I'd like you to try an oxygen molecule. Okay, now this one's going to be a little bit different than the first 2 because the elements are identical. We've got oxygen with oxygen. So let's go ahead and total everything up. Each oxygen is going to donate 6 valence electrons, so we got 12 electrons. And the first step is to connect it with bonds. So I'm going to connect an oxygen with an oxygen. And you might say, well, which one's the central atom? It's like, your choice, okay? It's completely symmetrical. So let's just go ahead and label the left one as the central and the right one as the non-central. This problem will work out exactly the same way if you reverse that, okay? But let's follow the steps, okay? We're going to complete the octet of the non-central atom first. So the non-central is over here. So to complete its octet, we're going to use these 6 electrons. So if I'm continuing my chart, the first step was to use 2 electrons on the bond. And then I use 6 more electrons on the non-central. And that leaves us with 4 electrons left over, and we're going to use all of the leftover electrons on our central atom. So on my central atom, I'm going to place all the leftovers. There were 4, and now I have 0 electrons left over. Okay. Now here's an issue. Okay, the non-central atom has a complete octet. 2, 4, 6 plus the 2 that are shared gets it up to 8. Okay, but the central atom, its octet is not fulfilled. Okay, even after I put the leftover electrons on the central atom, this does not have a complete octet. There's 2, 4, and then the shared electrons is only 6. So this is where step 5 comes into play. Okay, it says try multiple bonds if the central atom does not have a completed octet. I do not have a completed octet, so I have to try multiple bonds. Now I can't come in here and just draw a line because that represents 2 electrons, and I would no longer have 12 electrons in my model. I'd have 14, which would be completely wrong. So those electrons, where I try to do a multiple bond, those electrons have to come from someplace, okay? And it doesn't make sense to pull them from the central atom because it's the thing that has the octet that's not completed. So when you try multiple bonds, you got to pull electrons from the non-central atom, okay? So I'm going to take these 2 electrons that are currently unshared. They belong to the non-central atom. But I'm going to erase them and make them shared. And when I start sharing them, okay, this still has a completed octet. 2, 4, 6, 8 electrons. And now the central atom also has 8 electrons. 2, 4, 6, and 8. Okay, so this is how you would handle multiple bonds if your central atom, okay, does not have a completed octet. Okay, so that completes step 5, and then step 6 says don't forget your dipoles. Now let's talk about this problem. Okay, is there a dipole that exists between oxygen bonding with oxygen? Okay, I don't think so, because I don't think this oxygen is any stronger than this oxygen. In fact, their electronegativities are identical. So when they share electrons, they're going to fight over them, but one oxygen is not any stronger than another oxygen, and they're going to share their electrons equally. So no dipole signs here. Dipole signs are when the electrons are shared unequally, and in this case, they're being shared equally. So no dipole signs when you have a situation like this. Okay, we're going to ramp it up. I've got 2 problems left, and each of these problems are a little bit different. So I definitely want you hanging out to the end of the video. Okay, next one is going to be something that has a charge. Let's say I want to do the phosphate polyatomic ion, and it's a PO4 with a -3 charge. What makes this problem different is how we sum up the electrons, because now we have to pay attention to the charge. There's something up here in the upper right-hand corner. So I'm going to create my chart again, phosphorus and oxygen. 1 phosphorus, 4 oxygens. Phosphorus donates 5 valence electrons. The oxygen donates 6. So if I stopped right here and I added these 2 numbers together, I'd get 29. Odd number, ding, 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 ding. Remember, red flag, okay? Odd numbers means you're probably doing something wrong. And what I'm forgetting about is the charge. Now, if it's a -3 charge, that means electrons have come in to the molecule, okay, in order to give it a -3 charge. So we're going to add electrons in, and when we add those electrons in, we get, instead of 29, we get 32 electrons. And now that we have 32 electrons, I think everything else is going to run pretty much the same way as the other problems, okay? But take a look at the very end of the problem as well, because there is just a little nuance there as well, okay? So phosphorus is the singular atom, so that's going to be my central atom. And I'm going to bond it with 4 oxygens, 1 on each side. And that's going to use up 8 electrons. So 8 electrons were used up for the bonds. There's 24 electrons left over. They go to complete the non-central atom's octet. So 2, 4, 6 plus the shared gets me up to 8. Same thing for all the other oxygens. That used up, actually all of the electrons were all used up on the non-central atom. So there's none left over to place on my central atom. It's like, uh-oh, there might be an issue. But there's not, because when I look at the central atom, it has a completed octet, 2, 4, 6, 8 electrons. So it kind of just worked out again, okay? Now, I don't have to try multiple bonds because I have a completed octet, but I can't forget my dipoles. I got to compare where phosphorus and oxygen are because these electrons are not going to be shared equally between the two. Oxygen is up and to the right on the periodic table more, so oxygen is going to share the electrons unequally. They're going to be pulled towards the oxygen in all of these bonds. And then the last little nuance that I was talking about is typically when things are charged, we put them in brackets, okay, to remind the person, hey, 3 electrons came into this structure to complete it, okay? And if we didn't count the charge, there might be a hole here or a hole here or a hole here, meaning those octets would not have been completed, okay? So we typically would put this in a bracket, okay? Now, if I was going to go a little bit farther of like, hey, where are these electrons coming from, okay? Let me give you a small example, okay? Maybe they're coming from an element like aluminum, where these 3 electrons kind of entered the phosphate polyatomic ion so that everything could work out perfectly. So what type of bonding exists here? Well, we have ionic bonding because there's a transfer of electrons. These are arrowheads, okay? There's a transfer of electrons, but this portion over here, okay, is showing polar covalent bonding. So kind of interesting to see that a molecule can have 2 types of bonding that are going on at the same time. Now, since there is a transfer of electrons and we have cations and anions, we would say that this is an ionic compound, okay? But the phosphate part of that compound has polar covalent bonding in it. So just kind of wanted to bring something from the last lesson into this lesson with the ionic bonding. So when something is charged, just remember those electrons came from someplace, and if it ended up being a positive charge, those electrons would go to someplace because we can't create or destroy matter. Okay. Now, last problem, just a nice practice problem to make sure we understand all of this, and that's going to be carbon dioxide. So we got a carbon and 2 oxygens. The carbon donates 4. The oxygen donates 6. So we have a total of 16 electrons that we have to play with. The carbon is going to be the central atom, and I'm going to connect that with bonds to oxygen. I used up 4 electrons on the bonds. So there's 12 electrons left over, and I'm going to place those 12 electrons on the non-central atom, 2, 4, 6. 2, 4, 6, plus the bond gets it up to 8. So I use all of the electrons on the non-central atom. We might say, uh-oh, there might be an issue, okay? And this time there really is an issue, okay? Because the central atom, it does not have a complete octet. In our last problem with phosphate, the octet was complete. We didn't have to worry about anything. But this time, the octet is not complete, okay? And this is where step 5 comes back into play. It says try multiple bonds if a central atom does not have a completed octet. Central atom does not have a complete octet. There's only 2, 4 electrons on the carbon, and it wants to get up to 8. It wants to have a complete octet. So we have to try multiple bonds. Remember, we're not going to pull anything off of the central atom. We're going to pull them off of the non-central atom, and then we share those electrons. Now, that does not change the oxygen. It still has 2, 4, 6, 8 valence electrons. So its octet is still intact. But what we did help out was the carbon. It now has 2, 4, 6 electrons instead of 4. We're going to do the same thing on the other side because we need to get up to 8. So I'm going to erase those 2 unshared electrons, and now I'm making them shared. The oxygen still has 2, 4, 6, 8, and now my carbon has 2, 4, 6, 8, and it has a completed octet. Okay, so that's where the multiple bonds comes back into play. And of course, step 6, don't forget your dipoles. Carbon and oxygen do not share their electrons equally. Oxygen has a higher electronegativity, so we're going to make the dipole signs to say, hey, the electrons are being shifted towards the oxygen because they're not sharing their electrons equally. So this is the model that we have for carbon dioxide. And that kind of completes the lesson for covalent bonding. Okay? If you found this video to be informational, or if it helped you understand covalent bonding and the difference between nonpolar covalent and polar covalent, please like and subscribe. This helps the YouTube algorithm get this information out to other students that want to learn chemistry in a straightforward fashion.